Hey everyone, welcome back to another video. Today we're going to be jumping right in with some practice problems on what we learned in the last video, the Intro to Differential Equations video, which I'll link in the description below in case you missed. This video is specifically going to focus on the separation of variables method for solving differential equations. Let's look at this example to see what that really means. So, kind of in the name, the separation of variable method means we want to get each variable, whether it's x or y, onto its own side so that we can integrate it and solve the differential equation. So how would we do that for this specific problem? Well, we have dy over dx equals 2xy. So we want to get the y on the left side and isolated with the dy, and the dx on the right side and isolated with the 2x. So to do that, we're going to divide both sides by y and multiply both sides by dx. Doing that is going to give us 1 over y dy is equal to 2x dx. So nice and easy, we've got each variable on its own side, and we can go ahead and integrate. So integrating the left side, we know is going to give us the natural log of the absolute value of y, and integrating the right side is going to give us x squared plus c. Now we know that this plus c term has to exist because up here, we don't have any initial value or like set of points that the problem is asking us to satisfy in this differential equation. There's no condition that we're constrained to satisfying. We're just finding the general solution to this differential equation. So moving on, we're going to exponentiate both sides so that we can solve for y and simplify our overall solution. So it's going to become e to the natural log of the absolute value of y is equal to e to the x squared plus c. Using what we know about logarithms and the rules, we know that the left side is going to simplify to just being the absolute value of y. And the right side over here, we can write this as e to the x squared times e to the c. Awesome. Because that corresponds with our exponential rules. So we know that e to the c is the same as just another constant. E is a constant, c is a constant. We're raising a constant to a constant. So we can just write this and represent this as c. So now we have the absolute value of y is equal to c times e to the x squared. Awesome, this is looking a lot simpler than it was before. Now, we know that the absolute value of y just means that y is equal to plus or minus whatever it's equal to. Because since it's absolute value, we don't know if it's positive or negative. So we can rewrite this as y is equal to plus or minus ce to the x squared. Now, another way to oversimplify this, just to get a really nice answer, is to write, since c is just a constant, it doesn't matter if the constant is positive or negative, we can write to the side here that we have a new c term called c1, and it's equal to plus or minus c. Because at the end of the day, we're just representing the fact that there's a constant here. It's a general solution. We don't know exactly what that constant is. It's just important that we have the constant in the solution. So our final answer becomes y is equal to c1 e to the x squared. Nice, and that's how we solved our first separation of variables method problem. All right, guys, now we're going to try a problem that looks a little bit more complicated, but trust me, we're going to be able to solve the exact same way using the separation of variables method. So we see on the right side, we've got a y term that we want to isolate and get on the left side. We also want to get rid of the dx term that's in the denominator on the left side. So what are we going to do? We're going to multiply both sides of the equation by y and also by dx. This is going to give us y dy on the left side, and on the right side, it's going to give us x squared over 1 plus x cubed dx. Now we can integrate both of these sides of the equation pretty easy now because we've got each variable on its own side. And the left side, we know that's the easy integral. It's 1/2 y squared. The right side, however, we know that we can't really integrate this straight up. We're going to have to do a little bit of a u substitution here. So let's take this over here. And let's let u equal 1 plus x cubed. Then we take du, we know it's going to equal x squared dx. Sorry, 3x squared dx. Divide both sides by 3. We know that 1/3 du is equal to x squared dx. Awesome. So from here, we can go ahead and substitute that back into our equation. And we know that the right side is going to become the 1/3 times the integral of 1 over u du. Now let's solve that integral. We have 1/2 y squared on the left side still, but the right side is going to become 1/3 times the natural log of the absolute value of u plus c. Again, it's plus c because there's no required condition that we have to satisfy in the problem that we're being asked to solve. It's just a general solution. Anyways, going back to the problem, now we can plug in what we know u is, which we set to 1 plus x cubed. So this whole thing becomes 1/2 y squared is equal to 1/3 times the natural log of the absolute value of 1 plus x cubed plus c. Awesome. So now we're going to simplify this a little further. Let's take it over here. And we're going to multiply both sides by 2. And we're going to get y squared is equal to 2/3 times the natural log of 1 plus x cubed plus c. However, let's go ahead and call this c1. And we're going to denote that c1 is equal to 2 times c. Because since we multiplied the whole thing by 2, we could just write 2c, but it's easier to always represent your constants as just a single letter, but just denoting any changes that you made to the side. So we're going to say c1 is equal to 2c. Now we're going to take the square root of both sides to get our final solution to the differential equation. So square root of both sides, and that's going to give us y is equal to plus or minus the square root of 2/3 the natural log of the absolute value of 1 plus x cubed plus c1. And that's our final solution to the second problem. So you see, we might have had to do a little bit more calculus, but the same idea of separating the variables and integrating both sides still remained in solving this differential equation. All right, guys, let's go ahead and solve a little bit more of a complicated problem. At first, this thing looks really scary, but just try and see what you can do. Try and get the variables isolated on each side. Pause the video and come back and I'll explain it. All right, so to do this, we're going to have to do something called factoring by grouping, which I'm sure is something you've all done before in your Calc 1 and 2 classes, but let's get a little quick refresher on it just in case we forgot. So looking at just the numerator, we've got xy minus 2y plus x minus 2. Now, this thing on the left here, I feel like we could factor out a y there and get a y times x minus 2. So let's try that. The top is going to become y times x minus 2. And then this is just plus 1 times x minus 2. This ultimately simplifies to y plus 1 times x minus 2. And that's how we factored it by grouping. So what would the denominator be? Well, pretty much the same thing. We're going to factor out a y here. It's going to be y times x plus 3. And here it's a little bit tricky because we see minus x minus 3, but if we factor it out a minus 1, well then it would be minus 1 times x plus 3. If we distributed that minus 1, we'd have minus x and minus 3. So we know for sure that that works. So this is going to become y minus 1 times x plus 3. Awesome. So now we've got a way to rewrite this whole thing to something where the variables look isolated and it's a little more manageable regarding how we could separate the variables. So let's rewrite it. We're going to have dy dx is equal to y plus 1 times x minus 2 over y minus 1 times x plus 3. All right, beautiful. So from here, we know we want to get the dx on the right side with the x terms, and we want to get the y terms on the left side with the dy. So we could divide out the y terms from the both sides of the equation. So we're going to take these and divide both sides of the equation by this to get rid of it. And we know when we divide a fraction, it's like the same as multiplying by its reciprocal. So this is going to become y minus 1 over y plus 1 dy is equal to, well, the right side stays the same because we didn't touch it, except we're going to multiply both sides of the equation by dx. So x minus 2 over x plus 3 times dx. Awesome. So from here, we can integrate these. So we're going to put integral signs on both sides. Now the thing is, these also look like kind of tricky integrals. However, instead of doing long division or something weird like that, we're going to rewrite the numerators to match the denominators. That way we can have an easier integral. So what could y minus 1 be rewritten to match the denominator if we wanted the numerator to be y plus 1? Well, this is the same as the integral of y plus 1 minus 2, because 1 minus 2 is minus 1, so it's still the same as y minus 1 over y plus 1 dy. And we know that can be rewritten as the integral of 1, because y plus 1 over y plus 1, just these two, would be 1, minus 2 over y plus 1 dy. And with regards to the left side, to the right side, I mean, we do the same thing. So what would we do to get the x minus 2 on the top to match the x plus 3 in the denominator? Well, let's just write x plus 3 and see what we need to do to reset it back to x minus 2. So this would be the same as the integral of x plus 3 minus 5, because 3 minus 5 is negative 2. So that would be the same as writing x minus 2 over x plus 3 dx. And in the same way we did on the left, we can see that these are going to simplify to 1. So it's just the integral of 1 minus 5 over x plus 3 dx. Awesome. All right. So from here, we can just go ahead and integrate these. We're going to get the integral of 1 dy is y. And then we're going to integrate this part of the equation separately. And we know that this is the same as 2 times the natural log of the absolute value of y plus 1. For the right side, we're going to go ahead and integrate just the 1, which we know is going to be x, nice and easy. Then this is just going to be 5 times the natural log of the absolute value of x plus 3. And of course, what can we not forget? Because there was no initial condition we have to satisfy. This is a general solution, so we have to do plus c. And there's our final answer. It might look like a little bit of a complicated answer, but there's not really a clear way for us to get the y's just into a single y and have like an equation solution where it's just y equals something. So it's okay to leave it like this. As long as it's clear that everything is in terms of y, there's no y squared terms, nothing like that. But yeah, this is our final solution. All right, once again, let's try another problem that looks a little bit complicated, but we'll still be able to solve nice and easy. So here we've got e to the x minus y plus x squared times e to the negative y. So we might be looking at this and thinking, oh my gosh, like how are we going to separate the e to the x minus y term? How are we going to get just an x and a y out of that? Well, it's always important not to overthink, not to overcomplicate things. And remember our fundamental rules. We know from our exponential rules that e to the x minus y is the same thing as e to the x times e to the negative y. This is something we learned in pre-calculus and algebra 2. It's just how exponents work. So we can rewrite the equation as that. So we're going to have dy dx is equal to e to the x times e to the negative y plus x squared times e to the negative y. Now, what do we notice is the same here? Well, I see a e to the negative y term attached to every term on the right side of this equation. Right here, right here. So we can probably factor that out, right? So we're going to rewrite this again. It's going to be dy over dx is equal to e to the negative y times e to the x plus x squared. Awesome. Because as you can see, now we've got a way we could easily divide out this, because this is just the negative y term, and it's the only term on the right side of the equation that has y's in it. And inside this parentheses, I only see x's. So awesome. We've isolated the variables, and we can separate the variables just like the method asks for. So we're going to divide both sides by e to the negative y and multiply both sides by dx. So here we've got 1 over e to the negative y times dy is equal to e to the x plus x squared times dx. All right, Now we take the integral of this and the integral of this. And honestly, before we even do that, we know that this right here can be rewritten because we know 1 over e to the negative y is the exact same as just e to the y. So we've got e to the y dy is equal to the integral of e to the x plus x squared dx. So let's integrate both of those. And we know the integral of e to the y is just e to the y. We know the right side, e to the x is going to be just e to the x. And the integral of x squared is going to be 1/3 x cubed. Because this is the general solution, there's no initial value we're trying to satisfy. We're going to go ahead and add that plus c term. Awesome. So now from here, we can exponentiate everything. Sorry, not exponentiate everything. We're going to take the natural log of everything because the natural log of e to the y will simplify and give us just y. And we're trying to solve for an equation that's just y. So natural log of both sides, let me just write natural log of the whole equation. We're going to get y is equal to the natural log of the absolute value of e to the x plus 1/3 x cubed plus c. Awesome. And that's our final solution. Nice and easy. All right, guys, and to wrap up the video and finish strong, we're going to try something with trigonometric identities in the differential equation. So looking at this, this one's really simple with the way we separate the variables, but the way we integrate might not be as simple. Let's see how much we remember from Calc 2. So we're going to divide both sides by cosine squared y to get the y term isolated on the left side. So that's going to give us 1 over cosine squared y dy is equal to sine x dx. Awesome. Now we can integrate both sides. However, before we do that, let's recognize that 1 over cosine squared y is the same as secant squared y. And that's an important trigonometric identity from Calc 2 and Calc 1 that we have to remember for the remainder of our differential equations journey. It's going to come up a lot, so let's remember to commit all those trigonometric identities to memory. So this becomes secant squared of y. Whoops, that is really ugly. Okay, secant squared of y dy is equal to the sine x dx. From here, we can integrate nice and easy. So we know the integral of secant squared y. Well, it might take a little thinking, but what trigonometric term would have a derivative that's equal to secant squared y? Well, the answer to that would be tangent of y. And then the right side, that's the easy integral. We know that the integral of negative cosine x would give us sine x. And since, again, there's no initial value that we're trying to satisfy and no condition required, we're going to add the plus c because we know that this is a general solution. Now, we want to write our answer always, if possible, in terms of just y. So we want to get the left side to just be y equals. So we're going to have to take the arctangent of both sides to get rid of the tangent. So arctan of the whole thing, both sides. So we can get y, and then the right side is going to be arctan, which is the same as the inverse tan, of negative cosine x plus c. So yeah, that was a really simple problem in terms of separating the variables, but remembering our trigonometric identities and how to integrate those might be a little trickier and might require more jogging of our memory. But yeah, that's it for the video, everyone. I'll be posting more practice problems of different types of ways to solve differential equations soon. And let me know in the comments if anything was unclear or how I can improve in future videos. Thanks for tuning in.